Chapter 10. Properties of Solids and Liquids. Now we can investigate more complex chemical bonds and how they contribute to the structure of a molecule or a polyatomic ion. Once we have this basis of understanding, we can look at the differences in properties and reactivity of compounds. Electron dot formulas can be used to diagram the sharing of valence electrons in molecules of polyatomic ions. The presence of multiple bonds can be identified and possible resonance structures can be drawn. From the electron dot formulas, we can predict the three-dimensional shapes and polarities of molecules. Then we examine the different attractive forces between the particles of ions and molecules influence their physical properties, such as melting and boiling point. Finally, we discuss the physical states of solid, liquids, and gases and describe the energy involved in the changes of state. 10.1. Electron dot formulas. Electron dot formulas for the molecular compounds or polyatomic ions use the electron dot symbols shown in 10.1. For elements with 1 to 4 valence electrons, the dots are placed one at a time on the sides, top, bottom, and atomic symbol. For elements with more than 4 valence electron, each added dot is paired with one of the first 4 dots. Drawing electron dot formulas. When we draw an electron dot formula for a molecule or a polyatomic ion, we show the sequence of atoms, the bonding pairs of the electrons shared between atoms, and the non-bonding or lone pairs of electrons. From the formula, we identify the central atom, which is the element that has fewer atoms. Then the central atom is bonded with the other atoms, as shown in Concept Checks 10.1. Multiple covalent bonds and resonance. Up to now, we've looked at covalent bonding in molecules or polyatomic ions that have only single bonds. However, in some molecular compounds, atoms share 2 or 3 pairs of electrons to complete their octets. A double bond occurs when 2 pairs of electrons are shared. In a triple bond, 3 pairs of electrons are shared. Atoms of carbon, oxygen, nitrogen, and sulfur are most likely to form multiple bonds. Atoms of hydrogen and the halogens do not form double bonds or triple bonds. Double and triple bonds form when there are not enough valence electrons to complete the octets for some of the atoms in the molecule of a polyatomic ion. Then one or more lone pairs from the atoms attached to the central atom are shared with the central atom. For example, there are double bonds in carbon dioxide because 2 pairs of electrons are shared between carbon atom and each oxygen atom to give octets. The process of drawing an electron dot formula for carbon dioxide is shown in sample problem 10.3. Resonance structures. When a molecule or polyatomic ion contains multiple bonds, it may be possible to draw more than one electron dot formula. We can see how this happens when we draw the electron dot formula for ozone O3, a component in the stratosphere that protects us from the ultraviolet rays of the sun. To draw an electron dot formula for O3, we need to determine the number of valence electrons for each oxygen atom, and then the total number of valence electrons for ozone. Because oxygen is in group 6A, it has 6 valence electrons. Therefore, the compound ozone would have a total of 18 valence electrons. For the electron dot formula O3, we place 3 oxygen atoms in a row and identify the oxygen atom in the middle as the central atom. Using 4 of the available valence electrons, we draw a bonding pair between the oxygens on the end of the central O oxygen atom. 2 bonding pairs use 4 valence electrons. The remaining valence electrons, 14, are placed as lone pairs of electrons around the oxygen atoms on both ends of the electron dot formula, and 1 lone pair on the central oxygen atom. To complete an octet for the central atom, 1 lone pair of electrons from the end of the atom needs to be shared. But which lone pair should be used? One possibility is form a double bond between the central atom and the oxygen on the left. And the other possibility is to form a double bond between the central atom and the oxygen on the right. Thus, it's possible to draw two or more electron dot formulas for a molecule such as ozone or for a polyatomic ion. When this happens, all of the possible electron dot formulas are called resonance structures, and this relationship is shown by drawing a double-headed arrow between them. Experiments show that the actual bond lengths in ozone are equivalent to a molecule with a 1.5 bond between the central oxygen atom and each outside oxygen atom. In actual ozone molecule, the electrons are spread out equally over the oxygen atoms. When we draw resonance structures of molecules of polyatomic ions, the true structure is really an average of those structures. Table 10.2 summarizes this method of drawing electron dot formulas for several molecules and ions. Using valence electrons to draw electron dot formulas. Molecule chlorine has a total valence electrons of 14, forms single bonds to attach atoms, electrons are used. So electrons 14 minus 2, so there's 12 remaining. So the completed octet would be three pairs of electrons on both chlorines plus one single bond. Hydrogen chloride, there's one valence electron in hydrogen and 7 in chloride, so there's 8. 2 are used in the bond, that leaves 6, and the 6 all go on the chlorine. Water, there's 2 ones for the hydrogen plus 6 for the oxygen, that leaves 8. With a central oxygen and 2 hydrogens, that takes 4 electrons for the bonds, that leaves 4, and the 4 go on the oxygen. Phosphorus chloride, there's 5 for the phosphorus, 3 of 7s for the chlorine, and that's 26. There's 6 electrons used in the bonds, which leaves 20. So 3, 6, 9. 9 on the chlorine and 1 left on the phosphorus. Chloride ion is 7 for the chlorine, 3 oxygens at 6 each, plus 1 it being an anion is 26 electrons. So there are 3 bonds, so that's 6 electrons. That means there's 20 left. So there's going to be 9 on the oxygens and 1 on the chlorine. Nitrite ion, 5 for the nitrogen, 2 6s for the oxygen, plus the 1 for the ion is 18. So you have a central nitrogen ion with two oxygens. That's 2 bonds. 4 from 18 is 14. So that's 3 oxygens on one, 2 on the nitrogen, 2 on the oxygen with a double bond. And that's resonance with the oxygen on the other side.